Hello everyone, my name is Vageesha Sindhu and I am from BSc Chemistry Honours second year. We are doing organic chemistry topic, that is nitro compounds. Nitro compounds are an important class of organic compounds which may be regarded as derived from hydrocarbons by the replacement of one or more hydrogen atoms by nitro groups. Nitroarenes can be prepared rather easily and have been used as synthetic reagents since long. But nowadays even nitroalkanes are being prepared and used on a large scale. Structure of nitro groups. Nitro group is quite often represented as containing a double bond between nitrogen and one oxygen and a coordinate or dative bond between nitrogen and other oxygen. But actually nitro group is stabilized by resonance and is hybrid of two equivalent contributing structures. The resonance hybrid structure is confirmed by the fact that bond length of each nitrogen oxygen bond is 121 picometer or 1.21 angstrom, which is intermediate between NO single bond length 136 picometer or 1.36 angstrom and NOO bond length 115 picometer or 1.15 angstrom. In case of nitroarenes, resonance of nitro group with the ring can also take place, giving rise to additional contributing structures for the molecule. It will be interesting to note that nitro group is isoelectronic with carboxylate anion. Nomenclature of nitro compounds. Nitro compounds are named by writing the word nitro before the name of the parent compound. The number of nitro groups and their position are also suitably indicated as below, like nitromethane, nitroethane, 2-nitropropane, 2-nitro-3-methyl-butane, nitrobenzene, orthonitrotoluene, meta-dinitrobenzene, para-nitrophenol. Classification of nitroalkanes. Nitroalkanes are termed as primary, secondary or tertiary according as the nitro group is attached to a primary, secondary or tertiary carbon atom. Preparation of nitro compounds. Preparation of nitroalkanes. Nitroalkanes are usually prepared by the following methods. Vapor phase nitration of alkanes. This reaction involves the substitution of a hydrogen atom of the alkane by a nitro group. It is carried out in the vapor state by heating the alkane with nitric acid at about 700 Kelvin. Limitations of the process. During nitration of higher alkanes, all possible isomeric nitro products are formed. Moreover, rupture of carbon-carbon bonds also takes place, leading to the formation of nitroalkanes containing lesser number of carbon atoms. For example, nitration of propane results in the formation of a mixture of 4 nitro compounds, that is 1-nitropropane, 2-nitropropane, nitroethane and nitromethane. Due to the formation of complex mixture of products, this method is not used for the laboratory preparation of nitroalkanes. However, the method is widely used for the commercial preparation of the nitroalkanes, since they are used as industrial solvents only. Mechanism. The reaction is believed to involve the formation of free radicals, but the mechanism is not well established. Action of silver nitrite on alkyl halides. This is the method generally employed for the laboratory preparation of nitroalkanes. When heated with silver nitrite, alkyl halides undergoes nucleophilic substitution to form nitroalkanes along with small quantities of alkyl nitrites. This is because NO2 negative is an ambident nucleophile. However, the mixture of alkyl nitrites and nitroalkanes can be separated by fractional distillation. Oxidation of amines. When an amine in which the amino group is attached to a tertiary carbon atom is oxidized with potassium permanganate, a tertiary nitroalkane is obtained. Preparation of nitroarenes. Nitroarenes are almost invariably prepared by direct nitration of arenes. The nitrating agents generally used are concentrated or fuming nitric acid, mixture of concentrated or fuming nitric acid and concentrated sulfuric acid. This mixture is the most commonly used as nitrating mixture. Mixture of concentrated nitric acid, and acetic anhydride or boron trifluoride. Acetyl nitrate obtained by mixing nitrogen pentoxide and acetic anhydride. Nitrogen peroxide in the presence of anhydrous aluminum chloride. Choice of nitrating agent. The choice of nitrating agent to be used for nitration of a given compound depends upon the following two factors: nature of compound to be nitrated, number of nitro groups to be introduced. In the nitration of aromatic compounds containing electron releasing or activating groups such as NH2, OH and CH3, the reaction takes place readily at room temperature by employing concentrated HNO3. In some cases, even dilute HNO3 can be used. For nitrating compounds containing electron attracting or deactivating groups such as COH, or when it is desired to introduce more than one nitro group, a suitably strong nitrating mixture has to be employed and the reaction is carried out at high temperature. It may be remembered that nitro group itself is also a deactivating group. Nitrobenzene and metadinitrobenzene, for instance, can be obtained from benzene under the following conditions as shown. Mechanism of nitration. Nitration of aromatic compounds like other aromatic substitution reaction is electrophilic in nature and involves a nitronium ion as the attacking electrophile. Evidence in favor of the above mechanism. It has been shown above that aromatic nitration involves a stepwise mechanism. The nitronium ion, which acts as the electrophilic reagent, is generated in a preliminary step and brings about further reaction in two steps. The first step is a slow rate determining step involving the addition of nitronium ion in the aromatic ring to form a carbocation intermediate. The second step, which is relatively fast, involves the elimination of a proton from the ion intermediate ions by the heterolytic cleavage of CH bond. This mechanism has been fully supported by isotope tracer technique as explained below. If an aromatic compound labeled with deuterium, the heavier isotope of hydrogen having a mass of 2 atomic mass units, is subjected to nitration, it is found that the rate of substitution of deuterium is that same as that of ordinary hydrogen or protium. In other words, no isotope effect is observed. Since a carbon deuterium bond is broken more slowly than a carbon protium bond, the absence of isotope effect in aromatic nitration can be justified only if the rate determining step of the reaction doesn't involve any cleavage of carbon hydrogen bond. This means that the final step involving the abstraction of proton through the cleavage of carbon hydrogen bond can't be the rate determining step. Therefore, the step leading to the formation of carbocation must be the rate determining step, as it doesn't involve any cleavage of carbon hydrogen bond. Once formed, the carbocation loses the proton relatively fast to form the final product. The absence of isotope effect also rules out the possibility of a single step mechanism for nitration. This is because single step substitution can't take place without the cleavage of carbon hydrogen bond. As such, it must exhibit isotope effect, but this is not so in actual practice. Hence, aromatic nitration is a stepwise process in which the formation of carbocation is the rate determining step. Comparison of nitration of arenes and nitration of alkenes. It may be noted that nitration of arenes takes place at relatively low temperature, whereas nitration of alkenes requires a very high temperature. This may be due to the fact that the nitration of arenes involves the initial formation of an electrophilic reagent, while the nitration of alkanes is supposed to involve the initial formation of a free radical. The formation of free radical takes place through homolysis and requires stronger conditions than the formation of electrophile, which takes place through heterolysis. As such, nitration of arenes takes place more easily than nitration of alkenes. Nitroarenes can't be prepared by the action of silver nitrite or aryl halides because of the very low reactivity of aryl halides towards nucleophilic reagent. Physical properties of nitro compounds. Physical state. Nitroalkanes are colorless, oily liquids when pure. They have pleasant smell and are sparingly soluble in water. With the exception of few compounds including nitrobenzene, which are yellow oily liquids, all other aromatic nitro compounds are yellow crystalline solids. Nitrobenzene has an odor of bitter almonds and is known as oil of myrrhine. Solubility and density. All the nitro compounds are heavier than water. Nitroalkanes are sparingly soluble in water while aromatic nitro compounds are insoluble in it. They are however readily soluble in organic solvents such as alcohol and ether. Stability. When heated strongly, polynitro compounds decompose with explosive violence. Boiling point. Due to the presence of highly polar nitro groups in their molecules, nitro compounds have strong dipole-dipole interaction. That is mu is equal to 3 to 4 D. Consequently, they possess high boiling points much higher than hydrocarbons of comparable molecular masses. However, most of the nitro compounds are volatile in steam. The melting and boiling point of nitro compounds gradually increase with the number of nitro groups. Chemical reaction of nitroalkanes. Acidic nature. Tautomerism. Nitroalkanes containing alpha hydrogen atoms exhibit acidic behavior and form salt in the presence of strong alkalis. The acidity can be attributed to the fact that the nitro group has a strong electron withdrawing effect, inductive effect. The anion formed after the removal of the proton from nitroalkanes get resonance stabilized due to the ability of nitro group to accommodate negative charge. It is interesting to note that if salt formed by nitroalkane is acidified at low temperature, the oily drops of nitroalkane do not separate immediately, but we get another form of nitroalkane known as acinitro which slowly changes into the nitro form. This is due to the fact that primary and secondary nitroalkanes exhibit tautomerism. The tautomeric forms being nitroform and aciform are given below. The tautomeric equilibrium between the two forms lies almost completely towards the nitro form because it is stabilized by the resonance of nitro group. Acid nitroform is relatively stronger acid form than nitroform. An important feature of acid nitroform is that it can act both as an electrophile and a nucleophile. Unlike primary and secondary nitroalkanes, tertiary nitroalkanes do not have any alpha hydrogen atom. As such, they exhibit neither acidic character nor tautomerism. Reduction of nitroalkanes. Reduction of nitroalkane is one of their most important reactions. The reduction of nitroalkanes takes place in various stages. The product actually obtained depends upon the nature of the reducing agent and pH of the reaction medium. Thus, nitroalkanes can form different products on reduction. Reduction in acidic medium. When reduced in acidic medium, nitroalkanes form primary amines. Catalytic reduction or reduction with lithium aluminium hydride. Reduction with lithium aluminium hydride or H2 in presence of nickel palladium and platinum catalyst also yields the same product, that is amine. Reduction in neutral medium. If the reduction is carried out in a neutral medium, the hydroxyl amine derivative is obtained. The hydroxyl amines are readily oxidized to corresponding nitroso compounds on warming with Tollens reagent, which get reduced to metallic silver. This reaction is used as a test for nitro compounds under the name Baker-Millikan test. Hydrolysis. When boiled with concentrated HCl or H2SO4, primary nitroalkanes undergo hydrolysis to form carboxylic acids and the corresponding salt of hydroxylamines. Secondary nitroalkanes are hydrolyzed to ketones and nitrous oxide by boiling with concentrated HCl. Tertiary nitroalkanes are not hydrolyzed by acids. Neff reaction. When sodium salt of primary and secondary nitroalkanes are hydrolyzed by boiling with dilute sulfuric acid, aldehydes and ketones respectively are obtained. The reaction proceeds with the Ac-nitro form of nitroalkanes. In this reaction, the Ac-nitro form act as an electrophile. Action with nitrous acid. Primary, secondary and tertiary nitroalkanes exhibit different behavior towards nitrous acid. Primary nitroalkanes react with nitrous acid to form nitrolic acid which dissolve in NaOH to produce a red solution. Secondary nitroalkanes react with nitrous acid to form pseudonitrols which have blue color but do not dissolve in NaOH. Tertiary nitroalkanes and nitroarenes do not react with nitrous acid since they do not contain any alpha hydrogen atom. The above reaction can be used for distinguishing between primary, secondary and tertiary nitro compounds. Halogenation. When treated with halogens in slightly acidic alkaline solution, primary and secondary nitroalkanes undergo halogenation at alpha position. Nitromethane on chlorination in alkaline medium gives trichloronitromethane, also known as chloropicrin. Tertiary nitroalkanes do not undergo halogenation because they do not have alpha hydrogens. Condensation with aldehydes. Due to the presence of active alpha hydrogen atoms in them, primary and secondary nitroalkanes undergo aldol type condensation with aldehydes in the presence of a base to form nitroalcohols. Managed reaction. This is a condensation reaction which involves formaldehyde, ammonia and a primary or secondary amine and a compound having at least one active hydrogen such as primary and secondary nitroalkanes. The reaction can be used for preparing nitroamines, diamines, etc. Chemical reaction of nitroarenes. Nitroarenes are chemically rather inert compound. The nitro group is firmly attached to the nucleus and can't be replaced by other atoms or groups under ordinary conditions. Acidic nature. Unlike primary and secondary nitroalkanes, nitroarenes do not have any alpha hydrogen atom. As such, they do not exhibit acidic character of tautomerism. However, nitro compounds having two or more nitro groups attached to the benzene ring are somewhat acidic in nature due to the strong electron withdrawing effect of the nitro group on the benzene ring. Reduction. The most significant reaction of nitro compounds in their reduction under different conditions to give different products. As already stated, the reaction takes place in stages and the nature of final product depends mainly on the pH of the reaction mixture. We will illustrate the reduction of nitroarenes under different conditions with the help of nitrobenzene. Reduction in acidic medium. On reduction in acidic medium with an active metal and acids such as zinc and HCl or tin and HCl, nitrobenzene yields aniline. The mechanism proposed for the reaction involves a number of steps in which addition of electrons and protons takes place and the nitrobenzene free radical anion and nitrosobenzene free radical anion are formed as intermediates. Catalytic reduction. Reduction of nitrobenzene with hydrogen in presence of nickel or platinum catalyst also leads to the formation of aniline. Reduction in neutral medium. When reduced in neutral medium with zinc dust and ammonium chloride solution, the reaction stops at the hydroxylamine stage. Reduction in alkaline medium. On reduction in alkaline medium, nitrobenzene yields different products depending upon the nature of the reducing agent employed. These products are actually formed by further reaction between the primary reduction products, that is nitrosobenzene and phenyl hydroxylamine as shown. When nitrobenzene is treated with Na3ASO3 in presence of NaOH, azoxybenzene is obtained. When nitrobenzene is treated with zinc in presence of NaOH in methanol, azobenzene is obtained. When nitrobenzene is treated with zinc in presence of NaOH, then hydrazobenzene is obtained. There is sufficient reduction with lithium aluminium hydride. Reduction of nitrobenzene with lithium aluminium hydride also yields azobenzene. Electrolytic reduction. When reduced electrolytically in weakly acidic medium, nitrobenzene gives aniline, but on electrolytic reduction in strongly acidic medium, nitrobenzene yields para-aminophenol due to rearrangement of phenyl hydroxylamine. Electrolytic reduction in alkaline medium yields azoxybenzene, azobenzene, and hydrazobenzene. Selective reduction. In case of compound containing more than one nitro group, it is possible to carry out the selective reduction of one of the groups by employing a mild reducing agent such as ammonium hydrosulfide or sodium polysulfide. This reduction is known as Jenin reduction. Electrophilic substitution. Nitro group, being an electron withdrawing group, has a strongly deactivating effect on electrophilic substitution reaction of benzene nucleus. However, under strong condition, nitro compounds may undergo electrophilic substitution in meta position with respect to the nitro group. It may be noted that nitrobenzene doesn't undergo Friedel-Crafts reaction. Nucleophilic substitution. The nitro group has no doubt a deactivating influence on electrophilic substitution in benzene nucleus due to its electron withdrawing nature, but this is very electron withdrawing influence of nitro group makes the benzene nucleus liable to be attacked by nucleophilic reagents. Thus, unlike benzene, nitrobenzene on heating with sodium hydroxide gives small amount of ortho and para nitrophenols. Replacement of nitro group. In case of polynitro compounds, one of the nitro groups itself can be replaced by nucleophilic groups. Like para-dinitrobenzene on reaction with ammonia gives para-nitroaniline. The para-nitrobenzene on reaction with KOH gives para-nitrophenol, whereas para-nitrobenzene on reaction with C2H5ONa, that is sodium salt of ethanol, gives para-nitrophenitol. Thank you.